Okay, so let's begin again from here. The sound is clear. By x power 1 plus s dx, and this one you have. All right. Okay. All right. Thank you. So this one you have, the rest of this you have already done. This is 1 by s minus 1, right? And then, well, note that xi x is of the order x, right? So this integral converges absolutely for real part of s greater than 1, right? So we're going to use this. Okay, here. Okay, we'll do. So this part now we are dealing with the left hand side, and this becomes now the sum. Note that there was a sum inside and there was an integral. What we would do now, we'll switch the sum and the integral. Okay, and we are allowed to do this because of the absolute convergence of the integral. Okay, so this is sum over the prime powers integral from. Now note that this x was and pk was less than x, right? So if we switch the sum and the integral, that means the range of the integration should start from the prime powers, right? So pk to infinity, and here you have log p by x power 1 plus s dx, right? And this integral you have just done a while ago. So I mean the indefinite one, you still have to put the limits there. One limit would be just 0 and the other one is giving you what? What? Yeah, which one? This is, no, you are summing over pk, and yeah, in the integration the k is fixed, right? Because now you are summing over all the prime powers. You switch the sum and the integral here, right? And that you can do because of the absolute convergence of the integral. Okay, and now this pk is over all the prime powers. Okay, and for each prime power now this pk is fixed, right? So then inside you are getting, of course, and 1 by s, actually minus 1 by s, and what? P to the power. Okay, so upstairs you are getting log p, below you are getting minus s or s. Okay, have you checked? After taking the limit, you are getting a negative sign, right? So, wait a minute, there should be a minus s first, and after taking the limit, that negative sign will go away, right? So this is s times p power ks, right? So that becomes 1 by s times sum over pk log p by p power ks. Okay, and as you mentioned, this is just summing over the von Neumann function, right? So you could also write this as 1 by s summation over n lambda n by n power s, right? So let's consider this series lambda n by n power s. we have seen something in the first exercise session, if you recall. Lambda is, well, lambda n is equal to summation mu d log of n by d, right? D dividing n. In other words, lambda is, so this is recall from first exercise section, first tutorial, that lambda was mu star log, right? So that means the Dirichlet series associated with lambda, what we are seeing there, is equal to the Dirichlet series associated with mu times the one which should be associated with log. Okay. And we know something about the Dirichlet series associated with mu. What was that? Very good. It was 1 by zeta. Okay. So this is d log times 1 by zeta. Okay. So sorry, I didn't write all the a's. So here. Now what is this d log s? Can you write down the series and see? I note what this is. This is a sum over log n by n power s. N is running from 1 to infinity, right? Can you say anything about the series in terms of zeta? Indeed, yes. If you take a minus sign here, it is just zeta dash. Okay. Right? So that means what you have here is, wait a minute, at first. Here, that, okay, d log s, if we replace it by minus zeta dash s, this becomes then minus zeta dash s by zeta s, right? So here, this one then just becomes equal to minus zeta dash s by s zeta s, right? That is the first integral here. Okay, so this is minus zeta dash s by s zeta s, and here is a minus 1 by s minus 1. So in order to show that this is analytic in this region, we have to show that this is analytic in that region. Okay. At first, we are going to show that, I mean, we're going to check what happens at precisely at the point s equal to 1. Okay. And now recall from yesterday's tutorial, that was the third tutorial, right? We saw that zeta s has an integral representation. What was it? For, I mean, just using Abel summation formula, we got something, right? That is 1 by s minus 1, yes, plus 1 minus, let's write the exact expression. So this is from 1 to infinity, fractional part of x by x power 1 plus s, yes, dx, right? And this converges, I mean this integral converges absolutely for is greater than 1, and also note that at all the points on, so this we obtained that this is true for real part of s greater than 1, right? Okay, we did say that and we obtained it for s greater than 1, and then using the things that we have done on the what you call the axis of convergence, we conclude that it is so on the real part of s greater than 1. But note one thing, that except at this point s equal to 1, this integral doesn't have, I mean, this integral actually converges for all s which is greater than 0 in fact. So real part of s greater than 0, okay, and this, I mean, so in this region real part of s greater than 0, the only problem is at this point at s equal to 1, okay. So now we are concerned about the part where real part of s is greater than equal to 1, right? So in that region we have uh, we don't have exactly zeta s, but we have s zeta s below. But even s zeta s doesn't remove this pole from below, right? Because s zeta s would also be just like that, multiply to the s, and there you will get that 1 by s minus 1 plus 1 plus some terms, right? So 1 by s minus 1 again plus 1 plus s plus dot dot, okay, s times this one, okay. There wasn't an s yeah, right, there was already an s, so this is minus s square and this integral, okay. Okay, let's write it down. You're still here, right? Real part of s greater than 1. Is minus 1, right? If there is, okay, yeah, right, yeah, okay, thank you. So now note that this function is analytic on the, okay, as we saw that this is actually defined for all the points on the, for real part of s greater than 0, except possibly at the point s equal to 1 where it is having a pole, a simple pole with residue 1, right? So if you consider its Taylor expansion at the point 1, how does it look like? Yes, yeah, yes, s by s minus 1, which we have written as 1 plus this, okay. So it is s times this, which again we separate it as 1 plus 1 by s minus 1, okay. So at first, since zeta is, I mean, this integral is converging for in for all s with real part s greater than 0, so we can even write the Taylor expansion for zeta s, well, with a pole at s minus 1 plus, yeah, plus some constant a1 s minus 1 plus dot dot dot, right? I mean some convergent part, some and there is a pole at s equal to 1, okay. So zeta prime s will then have a pole like of order 2 at s minus 1 plus some b0 plus dot dot, okay. All right, so now we will have a similar expansion also for this one, because this is having I mean this is also having a simple pole at s minus 1. So maybe, I mean, since that is most relevant for us, so we just write that this has such a thing. Now consider this zeta prime s by s zeta s, okay, and we have a negative sign here, minus 1 by s minus 1. This we are going to consider now, okay. So this will become, okay, minus, okay, there's a negative sign here which can cancel with this one, okay, and then we have here 1 by s minus 1 whole square plus say b0 dash, that is the negatives of this one, okay. I am just not substituting all the symbols, just using dash for those, okay. This divided by this expression 1 by s minus 1 plus a0 plus a1 s minus 1 plus dot dot dot, okay, this minus 1 by s minus 1, right. Okay, so from here we get that sorry s zeta s minus 1 by s minus 1, this is equal to, well, if you do the necessary calculations, what we will have, this starts with 1 plus b0 times s minus 1 whole squared plus b1 dash times s minus 1 whole cube plus so on, okay, and below you have, well, this s minus 1 whole square should be multiplied below, so it should start with s minus 1 plus a0 plus e1 times s minus 1 plus dot 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 this minus 1 by s minus 1, right. Is right, thanks a lot, yeah. So actually we can take s minus 1, actually I mean, yeah, since just multiplying with s minus 1 would suffice, we can keep one s minus 1 out and write this as 1 plus, okay, here s minus 1 times 1 plus a0 times s minus 1, right. Yeah, we are only cancelling this one out, so after we multiply this by the bottom thing, a0 times s minus 1, a1 times s minus 1 whole square and so on, okay. Okay, all right, now this is 1 plus b0 dash s minus 1 whole square plus b1 dash s minus 1 whole cube plus dot 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 this thing minus, you take this up here, okay, this times s minus 1 first minus s minus 1 into 1 plus, I mean whatever is in the bottom, okay, right. Okay, actually we could have just taken, yeah, yes, after we I mean after we write here s minus 1 times 1 plus a0 s minus 1 plus dot dot dot. This s minus 1 term cancel. Oh, right. Yeah. Well, I mean, actually, we could just take this out, right? Thanks a lot. Yeah. Okay. So 1 by s minus 1 goes out, and then it is just this thing minus, well, 1 plus b0 s minus 1 whole squared plus b1 prime s minus 1 whole cube plus dot dot dot, this one minus whatever is left on the denominator, 1 plus a0 times s minus 1 plus dot dot dot. Okay, this divided by 1 plus a0 times s minus 1 plus dot. Okay, so what happens, this term gets cancelled, right? And then there is an s minus 1 term, the next one is I mean, there is an s minus 1 which cancels with this one. Okay, so that's what I wanted to show, that this one has a pole of order s minus sorry, residue, the pole of order 1 with residue 1 at 1, which cancels with this one. Okay, so this one just becomes b0 times s minus 1, wait a minute, no, this minus a0 times s minus 1 would come first. Yeah, minus, yeah, right, minus a1, sure. Okay, and below you have just whatever was the in the denominator, a0 s minus 1 plus dot dot. Now the denominator doesn't vanish at s equal to 1, right? Yes, how would? Yes. Oh, right, s minus 1 we have already, so it will be just s0. Yeah, right. And then this will be just s minus 1 and so on. Okay. All right. So this s minus 1 is not making a problem at the denominator because it's getting cancelled once we subtract this 1 by s minus 1. Okay. So in other words, we have just shown that this one is not having a pole at s equal to 1. Okay. Now we have to show that this doesn't have a pole on the real line s equal to 1, right? Well, on the real line s equal to 1, except at the point 1, this will not make a problem, right? So the only problem can come from here, right? So we have I mean, we are to the next step, into the next step, that is the zeta, I mean, this function zeta s does not vanish on the real line s equal to 1, on the line where the real part of s is equal to 1. It of course vanishes on the real line. As I said, on the left hand side of the real line, there are the trivial zeros at the negative even integers. Right? So yeah, maybe some part of the board we can clear up. Okay, so let's once recall what we have done till now. So I mean, earlier we have shown that pi x this is equivalent to xi x being asymptotic to x, and this is implied by the convergence of the integral from 1 to infinity xi x minus x by x square dx, and then this would be implied by the fact that the integral from 1 to infinity xi x minus x by x power 1 plus s is analytic on the region in the region real part of s greater than equal to 1, right? Thank you. Yeah, it converges. Yeah, yes, thank you. And that this is analytic in the region this, and then you see that this is equivalent to the fact that zeta s does not have a 0 on the line real part of s equal to 1. Okay. So we'll, I mean, it's this is actually this becomes actually the crux of the proof that we have to show that the real part of s is equal. I mean, this is not having a 0 on this line. Okay, so maybe we begin the afternoon session from here, that and we will give you many short exercises which leads to this point. Okay. Because it's already 1 and all of you must be hungry, so let's go for lunch. Thank you. So we see you again in 1 hour, okay, at 2 p.m. So today the afternoon session starts from 2.